Thanks a lot for the thanks a lot to the organizers for allowing me to present my work. It's always nice to be back to Bangalore, and I have always been privileged by attending all the most of the sort of meetings during my PhD times here. It's good to be back. Today I'll be talking about certain universality that we can see in granular systems, driven granular systems. This is a problem that we have been interested for some time, and I'll present some recent results. So, universalities are interesting because it tells us, or it allows us to simplify our understanding of physical systems by picking out relevant parameters in the process. So, one of the oldest scenarios in this connection is related to the equilibrium distribution of velocity distribution of molecular gases, which we know from good old days that the velocity distribution has a Gaussian form with this beta close to 2, beta equal to 2, irrespective of the molecular composition, or only constraint is that the collisions are elastic and which conserves the energy. And it can be also derived using kinetic theory or Boltzmann weight. Now, we would like to understand when we tweak the elasticity in the collisions and we consider inelastic collisions, whereby after each collision, the certain portion of kinetic energy is dissipated. Then what will happen to the universality? Is there any universality in this kind of inelastic collisions also for these many particle systems? So once we consider this kind of dissipative collisions, several other features emerge. That is because energy is monotonically decreasing upon each collision. There is no time invariant state for this system. Also, the relative velocities upon each collision decreases, and that allows the particles to spatially cluster. So there are no spatial homogeneities as in the molecular gases, and there is no time invariant state. So how to reach a comparable time invariant state, which is at the same time the system is homogeneous spatially. So this is usually done for granular or inelastic gases, which are basically the realistic systems are granular gases, which are the dilute versions of granular matter. So this is usually done by considering or supporting or compensating the kinetic energy upon each collision by using mechanical means, as shown here, where people actually vibrate the system, the container with where the particles are contained, or using electromagnetic or magnetic alternating fields. So one of the earliest sort of results on universality in this kind of driven inelastic gases came from theoretical perspective, where people assumed or modeled the driving using a white noise which is updating the velocities of those particles. Now, considering such a driving, no, this is for any dimensions actually. Now, in this case, considering this kind of driving, one can look at the master equation for the evolution equation of the velocity distributions, where we have integrated out the spatial degrees of freedom. And for large velocities, one can linearize the master equation, which is the Boltzmann equation. One can linearize it for large velocities. And assuming this form, one can show that beta equal to 3/2 gives the solution for this equation, irrespective of the properties of these inelastic particles. But there are several issues related to this kind of analysis, which I'm pointing out here. That is, this kind of universality is quite constrained with this kind of driving that we have used, because this operator is coming from this diffusive driving, and that is what allows us to get this 3/2. But if you consider this kind of driving, there is no steady state as such. And also, this driving is not very generic, because when you consider driving, it is usually the time scale of driving is comparable to the collision time scale. But here we are assuming that it is like the driving is done continuously. So we wanted to address this, and I should have said that this is sort of a very popular model, and there are even recent results that one could see that this 3/2 is seen in various experiments, or they predict that this 3/2 can be seen in various experiments. But there are various issues related to connecting these experimental results with the theoretical models, in the sense that usually we consider arbitrarily large tails, we can't get a good sampling, and hence fitting this kind of stretched exponents is always sort of a bit problematic. So it's good to have an analytical answer or an answer, as well as a comparable high or good sampling to get a consistent picture. So these are what we are addressing in our problem. So what we do is we look at the evolution equation for the velocity distribution, and consider a driving model which has a steady state, and ask whether we can have a solution for the velocity distribution whose dominant contribution is coming from the collision operator itself instead of the driving scheme, as we discussed in the previous slide. So this is the kind of master equation. So I have represented a one-dimensional version here, but one can write a two-dimensional version as well as here, two or arbitrary dimensions. But here one can see that this is the collision operator, or this is the terms that relates to the change in velocities due to the collision, and this part relates to the driving when we compare this kind of driving scheme. This driving scheme has a dissipative part which is proportional to the velocity, as well as a noise which comes from the external driving. And we consider a noise distribution which is of stretched exponential form. And this gamma, by varying gamma, we can change the kind of noise that is acting into the system. So if we want to consider a bounded driving scheme, we can look at gamma going to infinity limit, where this is like sharply decaying when compared to Gaussian. And we are not trying to solve this thing directly, but we look at the moments of these distributions. So we can write this equation in terms of moments, which comes as a set of series of functions of moments. And by assuming this an ansatz form for the velocity distribution in terms of a stretched exponential form, one can show that these moments in the large moment limit, large n limit, has a factorially increasing function, and so this series can be approximated to the maximal. Yeah, this delta is the collision rate. It is proportional to, so delta equal to 1 is the hard-sphere collision.
2 plus 2.
2, okay, yeah, I'm done. So now you have a set of, so basically we have a set of sums, and when we consider these two sums, the dominant contribution comes from the maximal term. And now one can solve self-consistently this equation for the moments and come up to the consistent relation for this beta. And these are the results that we get. So we have two universalities coming for this kind of driving, where when Rw is less than 1, which is the dissipative driving, we have a dissipative component. We find that for any gamma which is greater than 2, that is, which is bounded by Gaussian from above, we have a universality which is where exponent is equal to 2, and there is a logarithmic correction. And this is irrespective of the driving. So this contribution comes from the when the dominant contribution is coming from the collision part. Now, when we consider, and for gamma greater than or less than or equal to 2, the noise dominates, and you get the distribution which is same as the noise distribution. Similarly, for a diffusive driving, this Rw equal to 1, we have an exponential velocity distribution and another logarithmic correction. Now, to check whether this is true, one has to look at numerical simulations. And but numerical simulations, when we look at, one can see that we can't go to arbitrarily high precisions, as I pointed out before, because it's computationally very challenging. But what we did is we tried to consider a bias simulation where one could assign weights to trajectories and sample or perform simulations to get higher distributions at higher speeds. And what we can show from here is that for Rw equal to 1 case, that is the diffusive driving, we can get back our analytical result exactly matching. And yeah, so, but we are, just to conclude, so we have illustrated a universality for inelastic gases. One is the Gaussian universality with a logarithmic correction when the collision term dominates, and when the driving term dominates, we have an exponential driving. And exponential PDF is found in several microgravity experiments and magnetic driving setups. And we are currently trying to get for the dissipative driving case also. Okay, so these are the collaborators. Thank you.